Hello students, and welcome to today's lesson where we are going to be talking specifically about the IR spectrum questions, and I have an example of the IR spectrum questions like your paper 2 questions for this week that I'm going to run through just to help kind of give you guidelines for how to answer questions like these right here. Okay. So without much further ado, we're going to go ahead and take a look at the first question, and the first question here basically is having us interact with this right here, and it wants us to go ahead and specifically take a look at an IR spectrum, and it says that we have benzenol, and it's saying that this is a phenol, and we should notice right away that this has an OL ending, which means that we're going to go ahead and think of an alcohol. Okay, and it says briefly explain the characteristic features that we would expect in the IR spectrum, and it wants us to specifically reference the absorbance of light in that. Okay, and this first one, since it's an alcohol, we know automatically that an alcohol is going to be something that is going to have a strong absorbent peak. Okay, so that means that we're going to expect to see a strong absorbent peak. And that band is going to go ahead and be between the 3200 and the 3600 centimeter range. Okay, and with this here, this band is going to go ahead and represent the alcohol. Okay, so we're also going to want to go ahead and make sure that we reference that too. Okay, so we went ahead and we've now described one thing that we would see. We would also want to go ahead and kind of mark what makes this specific. Okay, and we're going to go ahead and describe this one as a wide or a broad base. Okay, now the other thing that we should go ahead and reference here. Okay, so this is basically what I'm thinking is 2 points right here. Now we're talking about the group for the OH group, which is important, and then we have our wide base here for the fact that it is an alcohol specifically. Now for the last point, what we're going to want to do is reference this kind of benzenol. Okay, and our benzenol is going to be where we have that carbon-carbon ring, where we have all those double bonds. We're going to go ahead and mention that specifically. So we'll go ahead and look at our chart, and we should see that in our chart it says that we should have some weak peaks at 1450 to 1650, representing the C double bond C. Okay, and this is going to go ahead and be our first question. And whenever we're referencing what kind of thing we're going to see, we're going to want to reference both the strength of the band, where it's at, and what we're going to see. So we want to be descriptive in our band itself there. Okay, and let's get that right under there. Okay, now the next question here is it saying that it was contaminant B was isolated in this sensor. Okay, it says that it's C4H2O2, and it says its IR spectrum shows a broad spectrum from 2500 to 3300. Okay, and a strong sharp peak at 1710. Okay, identify the functional group for V in this description. Okay, now we've already defined that we have one OH group. Okay, and how do we know that? It says that we have that broad, wide band. So that means that we have the OH group to go ahead and start us off. Okay. We also have a strong sharp peak at 1710, and that strong sharp peak is always going to be our C double bond O. Now, with both of these here, we're going to have to identify what thing has both a C double bond O and an OH. Okay, and in this case, this means that this is going to be a carboxylic acid. Okay, so we have our work here. We know that it's these two, so we're going to go ahead and say that compound V is a carboxylic acid. And we're going to go ahead and now explain how we know that. Due to the presence of an OH bond at the 2500 to 3300 centimeter -1 range, and a C double bond O at the 1700 range. So all that we've done here is we've essentially said, hey, these are the two things that is showing up on our presentation, on our device. Okay, our IR spectrum is showing these two ranges, and this is what we think it's going to go ahead and be because of that. Okay, and that's it for this question. Okay, we've identified what it is. We've explained how we know it. Our next question here is our classic percent composition question. So for this one here, we're going to go ahead and take a look at our percentages. Okay, we're going to go ahead and assume that they're 100%, and we're going to go ahead and start with the first one, which is going to be carbon here. And we're going to go ahead and take the carbon. Okay, carbon equals 70.59. And we're going to divide it by its mass, which is 12. We're going to go ahead and take the hydrogen next, and our hydrogen is 5.88. That's going to be divided by 1, and then we're finally going to take our oxygen, which equals 23.53. We're going to divide that by 16. When we divide the carbon by 12, we should get 5.88. When we divide the hydrogen, we're also going to go ahead and get 5.88. And then finally for the oxygen, we're going to go ahead and divide 1.47. We're going to go ahead and now say, hey, this is our ratio. This is how they come together. And we're going to divide them each by the smallest one. So we're going to divide them all by 1.47. Then when we do that, we're going to end up getting a number that's about close to 4. About close to 4 and 1. Which means that our empirical formula for this is going to be C4H4O. Okay, and that's it for this question here. Next, it's saying that compound Y, okay, compound Y does not react with Fehling's agents, okay? So, it does not react with Fehling's agents. So that tells us something already. It tells us that it's not going to end up being an aldehyde or a carbonyl group, okay? However, its IR spectrum shows a strong peak at 1735. Okay, so we're going to go ahead and take a look at this, and we have this strong peak at 1735. And we're going to take a look, and we're going to see a couple of things. Okay, first of all, we have this strong peak here. Okay, we also have this right here, and this right here is also going to indicate something for us. This shows that we also have a CO bond of some sort going on here. Okay, now this CO bond is going to go ahead and help us indicate that we have a carbon that's attached to a single oxygen. Okay, now we also should note that we're missing the OH bond that we would kind of expect if this was a carboxylic acid. We don't have this OH bond going on over in this area. We don't have this wide OH bond. So that means that we're going to have something that has both a double bonded O, okay, and it has a CO. The other thing we know is that it comes in this ratio of C4H4O. And we should immediately start to think, hey, wait a minute, I have 2 different oxygens here. I only have one here. I'm going to have to double this one here in order to make it work, okay? Because I need to have 2 oxygens. So now we're going to have C8H8O2 as our formula, and we have to figure out what kind of molecule is going to go ahead and have this kind of structure available to it, okay? And the first thing that I'm going to go ahead and be suspicious of is that we have a lot of H8s, and we've already talked about aromatic rings here before. So I'm going to go ahead and start specifically with drawing an aromatic ring. And I'm going to know that this is going to be only a total of 6 of our carbons, okay? And I know that I have to go ahead and put 2 oxygens on here, or 2 carbons. But I know that I'm going to have to put a double bond oxygen on one, and I have to have a single bond oxygen on another one. And now I have a problem here, because now this is essentially carboxylic acid, which we don't have here, and I'm still short 1 part, because I only have 1, 2, 3, 4, 5, 6, 7. Okay, so I'm going to put that last carbon here, and I'm going to go ahead and identify this one as a benzene. Okay, so we have a benzene because we have this ring, and then we have this ester group. Okay, and we have actually made what's called or essentially what's called methyl benzoate. okay? Because we got this benzene ring over here, and we have a methyl group right here, okay? Now, this is now our formula for Y. We're going to go ahead and keep that in mind, because our next question here is going to have us use that, okay? And it was even nice enough that it gave us formula Y here. It says that this decomposes into V and a final residue, Z. Determine the molecular formula for compound Z. And it even tells us what we're supposed to do. We're supposed to say that we have C8H8O2 to start with. And we're going to subtract from that C4H2O2 to get compound Z, which is going to leave us with C4H6. That's it. Okay, so we're left with just this one right here. Though I think I may have an error in my... No, it's all right there. Okay, so we have this here. This is our formula, okay, and this is going to go ahead and go right here. And then we go ahead and take a look here, and it says that it has the functional group on the first carbon, which is a nice thing for us to tell us. And then it says that this is, then we have this graph right here. And we're going to take a look here. We don't see that we have really anything special. We don't have our little come down here, our little points here where we would expect that we have a lot of double bonded carbons or an aromatic ring. This isn't very deep. We don't have any oxygens, but we do have this gap right here between these two. And this gap usually only happens when we're going to have some sort of double bond or triple bond. And when we have this big gap like this is indicating that we got a triple bond stretch. So we got a triple bond stretch going here. And it's even nice enough that it tells us specifically that this is on the first carbon, okay? Which means that we can now go ahead and draw our molecule. And we have 1, 2, 3, 4. 1, 2, 3, 4. And we know that this has a triple bond on the first carbon due to this one right here. Okay, now we're going to go ahead and make sure that it still meets our formula, which is C4H6. Okay, so this carbon, it has 3 bonds, so there's 1 there. This carbon has a total of 4 bonds. Okay, this one has 2. So we have 1, 2, 3. This carbon's going to have 3, 4, 5, 6. So we see that this matches this one, which means that we're happy. This is our answer here. Our final question has to ask us about these hybridized carbon states in compound Z. Okay, luckily we've already drawn compound Z. So now we just have to go ahead and say, all right, shoot, how many sp3 carbons do I have? And that's going to be carbon that has 4 things around it, okay, because it uses the S group and 3 Ps. Okay, well, this one is going to have 3 hydrogens around it. It's going to be sp3 hybridized. So sp3 hybridized, we have 1 here. This carbon, we said before, that has 2 hydrogens on it, and it's connected to 2 carbons. Therefore, this one is also going to be sp3 hybridized. And this one right here, we're going to notice that it only has this carbon that it's attached to, and this one. So that means it's only attached to 2 things. So it's only going to be sp hybridized. And the same is going to go for this carbon here. This carbon here also has only attached to 2 things. It's attached to the other carbon and that singular hydrogen. So that means that for this final question that we have here, the number of sp hybridized carbons is going to end up being 2. We have no sp2 hybridized carbons, and then we have 2 sp3 hybridized carbons. That is going to be it for this particular one, and I'm going to go ahead and tell you good luck on the next one.